Morning, everyone. My name is Sunfu Kai from Beihang University. Today, I will present our work, Spgemm, High Performance Sparse General Matrix Multiplication with Tensor Core Accelerated. The basic idea behind this work is simple. Tensor cores are very powerful for dense matrix computation. However, Spgemm is sparse and irregular. If we directly use tensor cores for Spgemm, many operations may be wasted on zero values. So, in this work, we focus on one main question. How can we make sparse matrix multiplication more suitable for tensor core computation? Our answer is to change the data layout first. We make sparse blocks denser and more regular, and then use tensor cores to compute them efficiently. This talk will cover the background and related formats of Spgemm, then introduce our Spgemm workflow, followed by the evaluation, conclusion, and future work. Okay, let's start with Spgemm. Spgemm means sparse general matrix multiplication. Here A, B, and C are all sparse matrices. That means most elements in this matrix are zero. Spgemm is an important operation in many areas. For example, it is used in scientific computing, graph analytics, and deep learning. But Spgemm is difficult to accelerate on GPUs. There are three main reasons. The first one is irregular memory access. The non-zero elements in matrix A decide which rows of matrix B will be used. So, the access pattern is often random. The second one is load imbalance. Some rows have many non-zero elements, while other rows have only a few. That makes it hard to give the same amount of work to each GPU threads or VOPs. The third one is high synchronization cost. In Spgemm, several partial results may write to the same output position on GPUs. This usually needs synchronization or atomic operations. So the parallel of efficiency becomes lower. The GPUs provide tensor cores. Tensor cores are special hardware units for matrix multiplication. They are very fast when the input is dense and regular. This gives us a chance to speed up Spgemm. But there is also a mismatch. Tensor cores prefer dense blocks. Spgemm gives us sparse and irregular blocks. If we simply divide a sparse matrix into face-size blocks, many blocks are still very sparse. Even a non-empty block may contain only a small number of non-zero elements. As shown in this figure, more than 60% of non-empty blocks have fewer than 32 non-zero elements. This means that many blocks are too sparse for tensor cores. If we directly use tensor cores, a large part of computation will still be spent on zeros. So, the motivation of our work is clear. Before using tensor cores, we need to improve the density of blocks. Before introducing our method, let's briefly look at existing sparse formats. This will help us to explain why a new format is needed for tensor core acceleration. The most common sparse format is CSR. CSR uses three areas: row PDR, core index, and value. Row PDR records the start position of each row. Core index stores the column index of non-zero elements. Value stores the actual non-zero values. CSR is compact because it only stores non-zero elements. It is also convenient for row-wise traversal. However, CSR is not ideal for GPU Spgemm. During multiplication, the access to matrix B is often irregular. Different rows also have different amounts of work. This causes low GPU efficiency. More importantly, CSR is one-dimensionally row-based format. It does not naturally match the two-dimensional dense blocks required by tensor core. The classical Gaussian method follows this row-based idea. It is generally and useful, but on GPUs, It suffers from irregular memory access, dynamic insertion overhead, and load imbalance. So CSR is a good storage format, but it is not a good match for tensor core computation. To improve CSR, previous work proposed tiled formats such as tau Spgemm. Tau Spgemm divides a sparse matrix into two-dimensional tiles. This improves locality and exposes more block-level parallelism. This is a useful step compared with pure CSR. However, tau Spgemm still has limitations. Many tiles may still have low density, so even inside a tile, many computations may still involve zeros. Also, tau Spgemm is mainly designed for CUDA cores. It does not fully match the dense block computation models of tensor cores. So the main problem is exciting formats are either compact but irregular, or block-based but still not. Now, I will introduce our method TC-Spgemm. The core idea is to reshape sparse matrix before computation, instead of directly sending the original sparse matrix to tensor cores. We first transform them into blocks that are more regular and denser. Then, tensor cores can do more useful work instead of wasting many operations on zeros. TC-Spgemm has 3 key components. The first component is block-wise similarity reorder for matrix A. Here, we reorder the rows of A so that rows with similar block structures are placed close to each other. This helps increase block density and improve locality. The second component is row block column compression from matrix B. Inside each row block of B, we remove empty columns and keep only active columns. This reduces useless memory loading and useless computation. The third component is a CSR-dense hybrid structure. At the block level, we still keep sparse indexing inside each valid block. We use dense storage, so the block can be directly used by tensor cores. Let's look at the first component in more detail. We use Chicard similarity to measure how similar two sets are. It's the size of the intersection divided by the size of the union. If the value is equal to 1, the two sides are very similar. If the close to 0, they are very different. In sparse matrix, we can use the idea to compare the block structures of different rows. However, simple row reorder is not enough. It may group similar rows together, but it may still fail to create compact blocks for tensor cores. For tensor core computation, the block level layout is more important. So, in our method, we focus on block column coverage, not just the original column index. This slide shows how we reorder matrix A. For each row, we first map its column index to block column index. For example, if the block size is 16, each column index is divided by 16. Then each row can be represented by the side block columns. After that, we compute the similarity between these block column size. Rows with similarity block column coverage are placed close together. To reduce the computation cost, we use Min-Hashi and RSH to find candidate groups. Then we use a gradient method to generate the final row order. After reordering, non-zero blocks become more concentrate. The block structure becomes more regular, and the effective block density becomes higher. The key point is, the step does not change the result of matrix multiplication. It not change the data layout to make the computation more efficiently. Next, let's look at matrix B. For matrix B, global reordering is not suitable. This is because the column index of A corresponds to the row index of B. If we reorder B globally, we may break the relationship. so we use local compression. We first divide B into row blocks. Inside each row block, we collect all column index that contain non-zero elements, and we sort them and remove repeat index. After that, we keep only these active columns. We also build a mapping from original column index to compressed local index. This removes empty columns inside each row block. It reduces useless memory access and increases the effective density of data sent to tensor cores. Because we keep the mapping, the final result can be still restored to the original matrix corridor rate. So this step reduces useless computation while keeping correctness. After rerouting A and compression B, we need a suitable data structure. We design a CSR-dense hybrid structure. At the block level, we use CSR-like indexing. For example, block row PDR and block code index record the position of non-empty blocks. This keeps the storage compact because empty blocks are not stored. Inside each valid block, we use dense storage. The block data is stored continuously, so it can be loaded efficiently into WMMA fragments. We also keep original index arrays, such as row ORI and co-ORI. They help us map local results back to the original matrix corridor rate. So CSR-dense has a simple role. At the block level, it keeps sparse. Inside each block, it provides a dense layout for tensor cores. This is the bridge between sparse matrix and tensor core computation. With CSR-dense, the kernel workflow becomes more regular. The workflow has 4 main steps. First, we generate valid block pairs. We only enumerate block pairs that really need to be computed. Second, we use warp level load balancing. One warp processes one block pair. This makes the workflow more regular and reduces thread divergence. Third, we use tensor cores for dense block computation. Each warp loads dense blocks into WMA fragments and performs block multiplication. Fourth, we restore sparsity. Tensor cores produce dense local output block, but the final matrix C should be sparse. So we identify non-zero results and map them back to global sparse index. In this way, we transform irregular sparse computation into regular block pair computation. This improves warp utilization and allows tensor cores to be used more effectively. Now I will move to the evaluation. We compare TC Spgemm with CUDA core baselines as a tensor core baselines. We also use ablatant studies to show the effective of each optimization, and we report the end-to-end performance. First, we compare TC Spgemm with CUDA core baselines, including CUSparse and TEL Spgemm. From the GFlops results, TC Spgemm achieves higher performance across matrices with different numbers of non-zero elements. Overall, it achieves 7.9 times average speedup over Sparse and 11.9 times average speedup with TEL Spgemm. Because most sparse metrics are highly sparse, the speedup plot on the right further show the distribution for metrics with sparse higher than 99%. That shows TC Spgemm can better handle irregular memory size and load imbalance by matching the data layout with tensor core computation. Next, we compare TC Spgemm with T-Sparse, which is also a tensor core-based method. Its comparison is important because it shows that simply using tensor cores is not enough. If the input blocks are still too sparse, tensor cores still waste many operations on zeros. TC Spgemm improves block density before computation, so tensor cores can perform more useful work. As a result, TC Spgemm achieves 13.7 times average speedup over T-Sparse. It confirms our main idea. Tensor cores can be fully used only when the data layout is regular enough and the block density high enough. The ablatant study shows that both row reordering and column compression are important. They bring 3.1 times and 2.6 times speed up respectively, which confirms that better data layout is a key reason for the performance gain. For end-to-end performance, TC Spgemm achieves 3.6 times average speedup over TEL Spgemm. Even including pre-processing overhead, it shows that the full pipeline is still efficient in practice. To conclude, TC Spgemm improves Sparse matrix multiplication by making Sparse blobs denser and more regular before tensor core computation. With row reordering, column compression, the CSR dense format, and a warp level kernel, it achieves clear speedups over exciting CUDA core and tensor core business. For future work, we will explore hybrid execution and adaptive block size selection. That concludes my presentation. Thank you for your attention.